Thank you. So I'm going to talk today about zero eigenvalue bifurcation points, such as the saddle node bifurcation. But those are boring words to most people, so I usually just call them tipping points. That's a loose term, it's not a precise mathematical definition, but it has the advantage that everybody knows more or less what you're trying to say. And to summarize my whole lecture, I'll just start with a small tipping point experiment under the watching eye of Salvador Dali, that was very interested himself in saddle node bifurcations. So the basic idea everybody understands: if you put a force to a system, the force may displace the state of the system, and usually the more force you put, then gradually you change the state of the system. But there are, as you all know, if you've been sitting on the chair too much, leaning to the back, there are critical points. And it's interesting when a system reaches such a critical point, it becomes vulnerable. It becomes fragile in a way. It loses resilience in the sense that if it's close to that point, even if a fly is coming and sits on this chair, that could be enough to call a really big change. So it's, as René Thom called a critical transition, a catastrophic shift. So this is not really catastrophic, of course, it's just a cheap table. But I mean, if it happens to the Earth system or to your brain or to society, such transitions can be really important. And in the early days of the work on this, and those are really early days, it's the 60s, the 50s that most of the work was done. People got really excited, but then they forgot about it because there were like big claims and they couldn't really substantiate that it was really important to real complex systems. But I think now we can substantiate that. And to illustrate how old that theory is, here is Salvador Dali again. And now it's the old Salvador Dali. This is actually the last picture of Salvador Dali, the last picture taken from him just before he died. And he dressed up one last time and he sat in front of the last painting he ever made, just to have him portrayed in front of something that he found was really very, very profound. And that is a painting of the catastrophe theory by René Thom in those days. He talked a lot to mathematicians, he talked to Prigogine, to René Thom, and I think it's telling that he as an artist felt this was so profound that his last painting is depicting that theory, and he wanted his last picture to be taken in front of that, of the theory of tipping points, if you want, but also with some nice elements of the violin into it, if you see. So you see that sigmoid shape. It's the same sigmoid shape that appeared in this 2001 Nature paper. So that was a paper about a very old theory. And I guess most of you know what it's illustrating. It's illustrating that systems can have alternative attractors, alternative stable states. And also that if the conditions change, maybe the system, represented by this ball, is sticking in the same state, but that state loses its resilience. It becomes smaller and smaller, the basin of attraction. And one of the former directors of IASA, Buzz Holling, he thought this was really important for ecological systems. And he said, well, we should really call that resilience, not the old-fashioned engineering resilience, but this is ecological resilience. It's like the size of the basin of attraction. And when an ecosystem loses that resilience, even a small thing can trigger a change. So again, 2001, a long time since the first mathematical ideas, but now we can really show that this kind of transitions happen in lakes, in coral reefs, in the climate system, in society. And the theory has a kind of revival in that sense. Of course, there are large implications because those are sudden transitions, they're big transitions, they can have large implications for society. And it's a challenging kind of change because you don't really see it coming. You see it coming for the table, you see it coming for a chair, but can you see it coming for a financial market, for the climate system, for the Arab Spring? That's not so obvious that you can see that. So, first of all, we can never predict them because the moment that that table is going to fall, it's always affected by small random things. We live in a stochastic world, and the final little push to systems that are close to a tipping point, it always happens randomly, stochastically. So we cannot predict that. But then the question I want to address today is whether we can actually say whether the system is becoming fragile. Is it whether you know, the size of the basin of attraction, the distance to that tipping point is becoming small? Is there any way we can say it? So that's like asking the question, can we find out whether a system is brittle without breaking it? Because that would be too easy, right? So, and then not just for the vase, but for societies, for the climate system, for instance. Well, if you have a perfect model, that's easy. But of course, we usually don't have the perfect model, and it's worse than that. We don't really understand most complex systems. We don't really understand the brain or society or the climate system. We only have hints of how it works. So I'm going to try to sell you the idea that perhaps we can, and perhaps we can because of some mathematical universal properties that systems have when they approach critical points. And those universal properties imply, I think, that there are generic indicators, generic early warning signals that could tell you whether you're reaching a critical point, in principle. So we discussed this in a little workshop with mathematicians, ecologists, social scientists, economists, climate scientists, and we all knew the old theory, and it's all, so in practice, the basics are well known for a long time, but we were wondering whether we could actually make this useful for understanding complex systems. We came up with a paper that summarized some of the ideas, and that quickly gave rise to a whole avalanche of papers, and those are only Nature and Science papers that came out since that time. So there was a whole excitement about it. So what was the basic idea? The basic idea is that if you perturb a system on the left-hand side, like it's a resilient system, you perturb it a little bit, and it'll recover. The ball will roll back. But on the right-hand side, when the system is close to losing that attractor, close to the saddle node bifurcation in this case, the valley becomes less steep. And if you displace that ball, it rolls back more slowly. Eventually, the slope becomes zero and it doesn't roll back at all. So this is the basic thing that's happening there, is that the dominant eigenvalue of the system that characterizes the return to equilibrium, it goes to zero. So that's the zero eigenvalue bifurcation. And this slowing down of the recovery is known as critical slowing down in the technical literature. So you can try that out. So if you're far from the bifurcation point, you'll see if you push it a little bit, you'll see a quick recovery. But if you're close, so on the right-hand side, then the recovery will take longer. So in principle, that's very nice, but we're not allowed to give experimental pushes to all systems. So we can't really do that for the brain and for the climate system. So what do we do then? Can we say something still? Well, perhaps, because each system is receiving little pushes around all the time, right? Your brain is receiving little inputs. The climate system is receiving the effects of volcano outbreaks and the changes in solar activity and all that. So complex systems are usually stochastically forced. And if you assume that regime of stochastic forcing remains the same, then if a system approaches the critical point, it will start behaving differently. The natural fluctuations in a system far from a tipping point are to the left, and to the right, these two panels illustrate the same system. This is a simulation close to the tipping point, subject to the same stochastic perturbation. And you see that the fluctuations become bigger, like the variance increases. But what's even more important is that the memory in the system becomes larger. The fluctuations become slower, they become more time correlated. So you see that on the lower right-hand side, if you plot the state at time t against t plus 1, it becomes more correlated. The system gets more memory, and this is just a reflection of this critical slowing down. So could we see that not only in a single differential equation, but also in more real world situations? Well, the first step is just to try it out in models. You can try it out in models that people believe are realistic, like the model of the thermohaline circulation that can collapse, or a model of lake that people really believe. And people have done that, and they find this critical slowing down indicators in all those models. But the model is still a model, so it's more interesting if you see it in real data. So we thought it's perhaps interesting to look at the climate history, because in the history of climate there have been some radical transitions, really. Like on the top left, you see the end of the greenhouse Earth. The Earth has been tropical for a very long time, and then, like 34 million years ago, we got ice caps, and it was a radical transition. So could you see that transition coming? Could you, if you just live in that time, you have this wonderful time series, could you predict how the time series would continue? Could you predict this? Well, perhaps if you, at the panel below that, you would have looked at the temporal correlation that tells you something about the slowness. Slowness was increasing in the Earth system before that transition. Or the end of a glaciation. This is the end of glaciation 1. Suppose you were living then. Could you predict what would be next? Could you predict this? Well, maybe if you had measured, as is depicted below, the temporal correlation in the system, the slowness. But of course, reconstructing the past of the climate, you never know really what happened. It's like a detective, never-ending detective story. So it's better if you show it in an experiment. And you can do that kind of experiments with lasers and all that, and that has been done before. But we showed it in a small ecosystem that we put in the lab, and we knew everything about that system. We pushed it to a tipping point, and we showed that close to the tipping point, there was a slowing down from the recovery upon small perturbations. So that was like a proof of principle. So some systems do seem to like obey the theory, so to say. And before I continue to other kind of phenomena, I want to stress that you don't only see the effect of critical slowing down in time series, you can also see them in the correlational patterns in networks. So we have many systems that are networks, and before a network radically shifts to a different state, you can also often see that slowing down reflected not just in time correlation, but also in correlation between the behavior of nodes. So one system that we studied is depression. Depression is seen as a network phenomenon now by psychiatrists and psychologists. We modeled that. If you're interested, you can look up that PNES paper. We also show in data that you can predict the probability that people will later in life get a depression from the properties of fluctuations in mood early on, and also the correlation between aspects of mood. So that is so far critical slowing down. But critical slowing down is something that you can only detect in systems that are close to equilibrium. And of course, there's many systems that are not close to equilibrium. There's many systems that fluctuate more wildly, either because they have cyclic or chaotic behavior, or because they're forced more strongly. So you cannot expect any signs of slowing down there. You can expect something else. You can expect flickering, because if you imagine this catastrophe fault that Salvador Dali also depicted, if you change the conditions gradually from the left to the right, as soon as that other attractor is appearing, you might occasionally visit that attractor. You flipper into it and you flipper out of it. We call that flickering. So in no way you're going to see critical slowing down there, because those systems are never close to an equilibrium where you could measure those aspects of the dominant eigenvalue getting close to zero at the point. You're far from equilibrium, but you can see other interesting things. Because if you see this flickering, it's like giving you a hint of an alternative state that maybe in the future you'll be in more frequently. And actually you can do even more than that. Valery Livina, working in the UK now, but Russian originally, got the idea that you could reconstruct actually those stability landscapes, those potential landscapes, if you have enough data. And she illustrated that on a time series of the climate. So you can look at the probability density of states, and that changes over time. So this is an illustration of a reconstructed change in stability landscape of the climate. Now, often we don't have very good time series of big complex systems, but nowadays we have satellite pictures, and that gives a lot of information in one picture. So you can also do the same kind of trick. You can exchange space for time easily, mathematically, and we have a lot of spatial data. So that's an interesting thing that you can use, and we decided to look at the transition from savanna to rainforest and vice versa. Those are thought to be alternative stable states. You're either in a savanna or in a forest state, and you flip between them. Well, we have a lot of spatial data on that. And in this picture, you see a plot of the tree cover in every square kilometer of the Earth, plotted against rainfall. And you see it's not a straight line, it's not a random pattern. Rather, there is this band on top, that's forest. And you see the forest is only there if it rains enough. And there is a very narrow band at the bottom, that's the desert. And in between there's this cloud, that's the savanna. And you can see that it depends on rainfall, which of the states is more likely. And you can use this kind of probability densities to reconstruct stability landscapes. So those are computed stability landscapes telling you how the stability, the resilience of tropical rainforest might depend on the rainfall. And you can use that to construct a map of the predicted resilience of tropical rainforest worldwide. And this is South America as an example. So of course that's a bit simplistic view. Really there are many more factors affecting the resilience. So it's complicated, but it's also nice because if there is more factors affecting resilience, you can use that to manage resilience. So you can use that, so to say, to create a safe operating space for the system. So the first time we developed that idea was for the global system, creating a safe operating space for planetary boundaries. Perhaps you saw that paper led by Jörn Rockström from Sweden. But we thought you could also apply it to ecosystems. The idea is there is maybe a critical stress condition where the system collapses, and you're probably uncertain about the precise response of the system and where it happens. So taking that uncertainty into account, there is a boundary, and only to the left side of that's a safe operating space. But of course that boundary for one stressor is usually dependent on how other stressors are affecting the system. And it's very often, for instance, that when you look at the effect of climate change on the vertical axis here, there is a critical climate for tropical rainforest where it might disappear. But that critical climate depends on other things, like whether you're harvesting trees from the forest and opening it. And that's a pretty universal thing. There are usually several local stressors that you can actually manage, you can affect them. And even if, as a country as Brazil, you cannot do alone much about climate change, or Australia cannot do much about climate change alone, but they can affect the resilience of the system by local measurement. So that's the idea of creating a safe operating space, building on those aspects. And we showed that for wetlands, for the tropical rainforest, for coral reefs, if you're interested to look into that further. So tipping points in complex system, the question, how can we see it coming? Can we prevent an unwanted tipping point? Or perhaps, can we promote a desired tipping point? Can we sometimes flip the system when we want it to flip? Can we flip people out of a poverty trap? Can we flip a turbid lake into a clear state? And there is, of course, in society, there's many examples of social traps where we really want to see a change, but we don't get out of it. Instead of that, we just improve the resilience of this little trap, but really there are better places arising around it, but we don't move to that. We're stuck in this trap. So can we see it in this context? What finally ended foot binding in ancient China? It was very difficult to get out of that trap, because if you wouldn't bind the feet of your baby, she would never marry. What finally allowed us to ban smoking in public places in many countries? It was very difficult. It was forbidden many times, but it didn't happen. In the end, suddenly it was forbidden again, and it happened. So what's determining the resilience of social traps? Can we understand the mechanisms? Can we perhaps reduce the resilience? And if it has been reduced, can we just briefly forbid smoking, and once you've then flipped the system into a different state, you don't need any enforcement, because actually now people that put up a cigarette in a public place in many countries, they're approached so aggressively by their peers that they immediately extinguish their cigarette. So when I think of complexity, I really like to think of a holistic way of viewing things. Science, of course, is very good at focusing at particular parts, but we have a very fragmented view of the whole world from science. So I think of complexity as a way of helping to defragment science. We always have had a holism. We have had ways of viewing the world, controlling it with rituals. And then we got science, which was much better, much more precise. But it was especially good at telling us things about very small elements of the world. We know everything about the CO2 molecule, but we don't understand very well what happens if we put that into the atmosphere. We know the neurons, how they work, but we don't understand very well how society behaves. So if you think of this fragmented view of the world, I think the challenge really is to make this holistic view, but not the old, vague holistic view, but try to combine insights into the detailed mechanisms with those new ways of looking at the whole to combine a sharper image of the whole. So thank you very much.